So, good evening to all the participants of the NPTEL course. We'll be starting the live interaction session now. Okay, so I will turn off my video and I will start sharing my screen. So, we'll be starting the presentation now. Okay. Okay. So welcome to the live interaction section 5 of this NPTEL course, Advanced Reinforced Concrete Design. And this course is brought to you by NPTEL, and the course instructor is Professor Surya Prakash from IIT Hyderabad. And this in this week we are going to be taking up the questions, some of the sample questions from week 5 of the course. Uh, so this is presently week 5 out of week 12 weeks of the uh, NPTEL online course. And this session is brought to you by me. My name is S. Lalit Sagar. I'm a doctoral candidate and PMRF fellow in the Department of Civil Engineering at IIT Delhi. Okay, so this will be the broad agenda for today's session. So, as most of you might be aware, so we have started with the module 5 of this NPTEL course, and module 5 is on the behavior and design of reinforced concrete members and flexure. And so this particular module has several parts. So we are going to be dealing with module 5.1 and 5.2. That is the first two parts of the module 5. Okay. So before proceeding to the question and answer, that is the sample question and answer, I would like to uh, spend little time on explaining, on discussing as to what was covered in this week's module, that is module 5.1 and 5.2. So in module 5.1, we discussed about the background to the flexural theory and provided an overview of the moment curvature analysis. Specifically, we tried to understand what would be the behavior of the reinforced concrete members and the flexure. Then we tried to derive the equations based on the governing equations based on the elastic beam theory. Then we derived the equivalent stress block parameters in order to determine the moment capacity and the curvature corresponding to the different levels of concrete, right? And then we explained what is essentially the moment curvature analysis. So in the last week, that is in module 4, that is for the discussion of the axial members, we perform the force deformation analysis. Okay, considering different values of uh, strains, axial strains in concrete. So similarly, we have performed the moment curvature analysis in this particular uh, uh, week's module, and we discussed the different types of failure in flexure. Uh, that is the brittle failure or the ductile failure, corresponding to the various types of cross sections. That is the under reinforced cross section, or the balanced cross section or the over-enforced cross section, and what are the different types of failures that can be expected from these different types of cross section depending on the percentage of reinforcing steel that is being provided. Okay, and in module 5.2 we studied about the effects of concrete strength and reinforcement ratios on the moment curvature analysis. So basically how the properties, the mechanical properties of the constituents of the cross section, that is uh, the mechanical properties of the concrete that is being used and the mechanical properties of the reinforcing steel, how that influences the moment curvature behavior or the moment curvature analysis. Okay, so in that we started with uh, the drawing of the moment curvature curve for an under-reinforced section. Then we compared the moment curvature curves for an under-reinforced cross section and a balanced section, and finally an over-reinforced cross section. And then we understood the effect of reinforcement ratios on the moment curvature behavior. So that is when we perform the moment curvature analysis and plot the moment curvature diagram. So how the shape of the plot varies depending on the reinforcement ratio. That is what we looked at. And then we looked at the effect of the compressive strength of concrete on the moment curvature behavior. So what would be the influence of varying the compressive strength of what would be the influence of varying concretes having different compressive strengths on the moment curvature behaviors? Okay, so we looked into that aspect as well. Now, having completed modules 5.1 and 5.2, we will be going ahead and we are going to be solving some sample problems based on the theoretical aspects as well as the numerical aspects covered in this week's module. Okay, and without any further delay, so let us start with the sample problems for this week 5 of the live interaction session. Okay, so first we are going to start with a conceptual question. When a beam is subjected to a flexure, when a beam is subjected to flexure in a 2D plane, what happens to the longitudinal and the transverse fibers? Okay, so there are 6 options. Okay, kindly think for a few minutes and let me know what would be the right answer. Yes, so I think we can have a look at the solution now. Okay, so let me read out the options first. The longitudinal fibers elongate and the transverse fibers shorten. Okay. Second option is longitudinal fibers shorten and transverse fibers elongate. Okay. Just give me okay. We can continue. The third option is longitudinal fibers rotate and transverse fibers shorten. Option D is longitudinal fibers elongate and shorten and transverse fibers rotate. Option E is longitudinal fibers rotate and transverse fibers elongate. Option F is longitudinal fibers elongate while the transverse fibers remain the same. So the correct option among the correct answer among these options is option D. Okay, so now let us look at a small let us look at the diagram which can explain what is happening to the longitudinal and transverse fibers of a beam that is subjected to flexure. Okay, so we can consider uh, this diagram. So this is the undeformed shape for the configuration. So the neutral axis is that axis, so which does not undergo any change uh, in the length of the longitudinal section. Okay, so the longitudinal fiber does not undergo any change in the length. So when the beam is subjected to a sagging bending moment, the fibers that are above the neutral axis tend to shorten, while the fibers below the neutral axis tend to elongate. Okay, which is why we can say that the longitudinal fibers elongate and shorten. Okay, now what is happening to the transverse fibers? So the transverse fibers uh, are perpendicular to the neutral axis. Okay, so we are assuming that they remain plane, they remain straight, however, but they are rotating. Okay, maybe uh, except a few except one a small portion of the beam at the center which moves vertically downwards, we can expect most of the transverse fibers to rotate uh, rotate in this direction. Okay, rotate in this plane, in this 2D plane. So out of the 6 options that are considered, we can say that the option D is correct, where the longitudinal fibers elongate and shorten while the transverse fibers rotate. Moving forward, let us look at the second question. Okay, so the second question is also a conceptual question. Which of the following statements is or are incorrect about the neutral axis or the neutral layer of a rectangular steel beam subjected to flexure? Okay, so there are 4 options. Kindly go through them and let me know what would be the correct response. Yeah, so we have connected back to the call. Let us continue with the discussion. So, uh, which of the following statements is or are incorrect about the neutral axis or the neutral layer of a rectangular steel beam subjected to flexure? So, remember that out of the four options that are being given, we need to identify the incorrect statements. So now let us look at each option one by one. Neutral layer is a vertical layer along the length of the beam and does not undergo any change of length when subjected to flexure. Okay. Second option is neutral axis is the line of intersection of the neutral layer with the transverse section. Okay. The third option is position of the neutral axis in the cross section varies along the length of the member. And the fourth option is locating the neutral axis is essential to determine the moment of resistance and curvature of a cross section. Okay. Out of these, option A and C are incorrect. Okay. So now let us look at the explanation. So when the beam is not in the flexure, the neutral layer remains horizontal. Okay. So this is the neutral layer, which is shown by the dotted line. But when it is subjected to flexural load or the lateral load, okay, which is perpendicular to the neutral layer, it tends to bend as a curve, okay, and so the neutral layer is a horizontal layer along the length of the beam, and it undergoes change of length when subjected to flexure, okay, and the second option is correct because neutral axis is the line of intersection. So when you see in the elevation, this is the neutral layer, but when you consider the cross section, okay, the intersection of the neutral layer along with the transverse section, that is called as the neutral axis, as you can see in this particular transverse section. So option B is correct, and option C states that the position of neutral axis in the cross section varies along the length of the member. That is incorrect because let us say that at this particular length, whatever is the depth of the neutral axis, that is going to remain more or less same along the entire length of the beam. Okay, that is one of the assumptions that we make in order to simplify the flexural problem. So option C is incorrect. Option D states that the locating the neutral axis is essential to determine the moment of resistance and curvature of a cross section. So option D is correct. So uh, ultimately we can say that out of the four options, option A and C are incorrect, but the options B and D are correct. Moving forward, we have the third question, which is again based on the theory of the elastic beam theory. According to the elastic beam theory, the relation between the longitudinal strain and the curvature is given by dash. Okay. So we need to specify based on the elastic beam theory, what is the relation between the longitudinal strain and the curvature. Okay. So here we have used several variables. So I'm going to read it out for better clarity. R is the radius of curvature. Okay, R is the radius of curvature. Phi is curvature. Epsilon is the longitudinal strain. Y is the distance of the fiber from the neutral axis, and L is the length of the beam. Okay. Kindly take a few minutes and let me know what would be the correct response. Okay, so now let us look at the correct response, right? Correct answer is option B. Okay, so we might have already seen in this week's lecture uh, that we derived the relation between the curvature phi, radius of curvature, and the longitudinal strain along with the length of the beam and the distance of the fiber from the neutral axis. And based on the elastic beam theory, we can say that based on our derivation, the curvature phi is equal to 1 by r, where r is the radius of curvature, is equal to epsilon by y. Again, epsilon is the longitudinal strain and y is the distance of the fiber from the neutral axis. Okay, so we can proceed to the next question now. Okay, so again, this is again a continuation, you can say, from the previous question. So according to the elastic beam theory, the relation between the curvature of the beam and its bending moment is given by dash. Okay, so there are 5 options. So please take a few minutes and let me know what would be the correct response. So in the previous question, we established the relation between the curvature phi and the radius of curvature r, and then the longitudinal strain, length of the beam, and the distance of the fiber from the neutral axis. Now we need to establish the relation between the curvature, the radius of curvature, uh, and the bending moment along with the flexural rigidity term EI. Okay. Okay, now let us look at the answer. So the correct answer is option B, where the curvature phi is equal to 1 by r is equal to m by EI. So how did we develop this equation, right? So first we integrated the axial stresses for the entire cross section and determine the resultant axial force, right? And then we uh, so please note that sigma xx, sigma xy, they are basically the stress components acting on this particular uh, cross section. And when we integrate the stress components over the entire cross sectional area, we obtain the stress resultants. Okay, so the stress resultants are the axial force F, the shear force V, and the bending moment M. Okay, and we know that by the Hooke's law, sigma xx is equal to Ex, where E is the elastic modulus into epsilon xx, right? And we are going to substitute this epsilon xx uh, in terms of the term y. Y corresponds to the distance of the layer from the neutral axis, and r corresponds to the radius of curvature. And then when we integrate this term, we obtain this relation where phi curvature is equal to 1 by r is equal to m by EI. Okay. So the correct answer for this particular question is option B, that is phi is equal to 1 by r is equal to m by ei. Okay. Okay, so we'll move on to the next question now. So the fifth question is, which of the following flexural failure modes are brittle in nature? Okay, so we have six options. Kindly take a few minutes and let me know what would be the correct response. We need to identify which of the following flexural failure modes are brittle in nature. So we have six option, six options. Option A corresponds to tension failure only, that is the failure of the longitudinal rebars. Second option is compression failure only, that is the compression of the concrete in the compression region of the beam. Option C is balanced failure only, that is when the compressive stress in concrete is reached at the same time when the yield stress of the reinforcing steel is reached, that is the balanced failure. Then we have the tension and balanced failure. Okay, that is the failure of the rebar and the balanced failure of both the concrete and rebar. Then we have the compressed and balanced failure, that is compression failure of concrete and balanced failure of concrete and rebar. Then we have combination of all the three, that is compression, tension and balanced failure. So out of these six options, the brittle modes of failure are option E. Okay, option E, which corresponds to the compression failure of concrete and the balanced failure of the concrete and rebar, those are the brittle modes of failure. Okay, let us look at the explanation now, right? So we have in this particular slide the depiction of the balanced failure, and we here we have the depiction of the compression failure, that is the strains in concrete and the reinforcing bar. So as I already mentioned, so the balanced failure is one where when you go on applying the flexural loads, there comes a point where the crushing of concrete takes place in compression and the yielding of steel rebars takes place under tension. Okay, so when the beam is provided with balanced reinforcement, as we discussed, compression of uh, the compression the compressive failure of concrete takes place, and at the same time the yielding of steel rebar takes place, and this mode of failure is brittle and it is sudden and it is therefore not allowed by the IS code. Okay, because um, it is specified in the IS code that before beam undergoes failure, it should give sufficient warning through excessive deformations. Okay, so that we can, um, it is less harmful of the two modes of failure, that is the brittle failure and the ductile failure. We want to design the reinforced concrete members and systems in such a way that they undergo sufficient deformation before failure and give a sufficient warning or ductile mode of failure is preferred over the brittle mode of failure. So that is why balanced failure comes under the category of brittle mode of failure. Then we have the compression failure. So here, as we can see that the length of the depth of the neutral axis is greater than xb. Xb corresponds to the depth of the neutral axis corresponding to a balanced section. So we can see here that the reinforcing steel under tension has not undergone yielding yet, but the strain in concrete has undergone the compressive strain, as a result of which the concrete crushing takes place, and it is known as a brittle mode of failure. And again, as I explained previously, uh, for the same reason that the mode of failure is brittle and sudden, the balanced failure is not permitted, and similarly, the compression failure is also not permitted because of the inadequate deformations in the beam. Okay. Moving forward, we'll proceed to the next question. So, question 6, we are going to be starting the numerical problems now. So, I'm going to read out the data pertaining to this particular problem. So, for a rectangular reinforced concrete beam having a width of 250 mm and a depth of 450 mm, okay, which is having an effective cover of 50 millimeter, and the mean cylinder strength, that is F prime C of concrete, is given, that is 30 MPa, and the beam is reinforced with 4 steel rebars of 20 mm diameter. Okay. Now the question is, considering the concrete strain of 0.005, what would be the moment and curvature corresponding to this concrete strain? Assume Fy is equal to 500 MPa, and kindly try to solve this problem and let me know what would be the correct response. Okay, let us start solving the problem now, right? Let me take out my tablet and okay. Right. So we'll draw the cross section of the beam first, right? So we have the cross section of the beam. So the width of the beam is 250 millimeter, the depth is 450, right? We have the area of steel. We're going to calculate that. And the effective depth is 400 millimeters. Okay. Now we have F prime C is equal to 30 MPa. F prime C is equal to 30 MPa and Fy is equal to 500 MPa. Okay. And let us calculate the AST now. That is the area of steel reinforcement. AST is equal to 5 by 4 into 20 square into 4. That would be, AST is 1256.64. 1256.64 mm square. So the question is, like, how do we go about solving the problem and determine the moment of curvature and the moment and the curvature, right? So let us consider the cross section now. Okay, so we already have the diagram over here. Now, basically, in order to determine the curvature or the moment, we need to locate the neutral axis first and determine the resultant forces. Okay, so so we need to locate the depth of the neutral axis based on a trial and error method, where we are going to obtain equal forces in compression and tension so that the cross section is in equilibrium. Now I have developed an Excel sheet in order to do the same. Okay, so we will take it up for the highest strain values, but now let us consider that uh, the value of x is how much? Okay, let us just check over here. So B is 250 millimeter, D is 450, and the effective depth is 400 millimeter. AST is 1256.64, right? And it will all automatically calculate the percentage of the steel reinforcement, and the compressive strength of concrete is 30 MPa, right? And 0.005. And now let us try value of x value of 138 millimeter. Okay, so we see that corresponding to a depth of neutral axis of 138 mm, we're able to balance both the tensile force in the reinforcement and the compressive force in the concrete. Okay, let us proceed by considering this x value, and let us see what is the value of m and phi that we are going to get eventually. Okay, right. So let's get back slide. Okay, so we'll consider x is equal to 130, sorry, 138 millimeter Now, let us calculate the strain in the rebar. By similar triangles, we have here epsilon c, and here we have epsilon t. Okay, now by similar triangles, we have epsilon c by x is equal to epsilon t divided by d minus x. Okay, let us substitute the values and find out what is the epsilon t that we are going to get. 0.0005 divided by x, 138, is equal to epsilon t. What is the value of d? D is 400. 400 minus x is 138. So we have epsilon t is equal to 0.00095. 0.00095. Okay, we're going to get this epsilon t. Now let us calculate what would be the corresponding tensile force. Okay, P is equal to epsilon t into ES, because this is still in the linear range, that is less than 0.0025, which corresponds to epsilon y, or the yield strain. Okay, so when we multiply this value of strain with the elastic modulus of steel, we obtain the tensile force as how much? 238.6 kilonewton. 238.6 kilonewton is the tensile force in the rebar. Now let us calculate the compressive force. We know that based on the stress block parameters. Okay, I'll draw the stress block parameters just for the reference, right? So we are going to be uh, converting the stress block into an uh, equivalent rectangular stress block. Okay, where we have uh, yeah, we have CC is equal to alpha 1 into F prime C into beta 1 into X into B. Okay, so here alpha 1 and beta 1 are the uh, some of the factors which determine the which corresponds to the concrete stress block. Okay, and how do we determine these values, right? So we have beta 1. I'm going to take a different color for a better contrast, right? We have beta 1 is equal to 4 minus epsilon c by epsilon prime c divided by 6 minus 2 times epsilon c by epsilon prime c. Okay, now we know that epsilon c is equal to 0.005, and then we can consider epsilon prime c as 0.002. Okay, please note that it is not, there has to be one more additional zero over here. Sorry, 0.0005. Substituting, we get value of beta 1 is equal to how much? 0.6818. 0.6818. Okay, then we have the expression for alpha 1. I'll take a different color once again for better contrast. Now, right, we have alpha 1 is equal to 1 over beta 1 into epsilon c by epsilon prime c minus 1 by 3 into epsilon c by epsilon prime c whole square. Okay. Now, when we substitute the value of beta 1 epsilon c epsilon prime c, we get epsilon 1 is equal to how much? 0.3361. Okay. Now, let us go back and find out the resultant compressive force over here. So, when we substitute the value of alpha 1 is equal to 0.3361, f prime c as 30, beta 1 as 0.6818, x as 138 millimeter, and b as 250 millimeter, we obtain the value of the resultant compressive force or Cc as 237.2 kilonewton. Okay, so there is a slight mismatch between the resultant compressive force and the tensile force, but still we are going to proceed with this approximation and go ahead and calculate the moment of resistance and the curvature. Okay, now because of the paucity of space, I'm going to come back to this particular slide, and we have the equation for the moment capacity as m is equal to cc into d minus beta 1 into x divided by 2. Okay, now when we substitute the value of cc as 237.2 kilonewton, d is 400 millimeter, beta 1 is again 0.68, and x is 138 millimeter. When we plug all these values, we obtain the value of m as 83.72 into 10 to the power 6 Newton millimeter, or 83.72 kilonewton meter. And the curvature phi is given by the strain in concrete divided by the depth of the neutral axis, that is 0.0005 divided by x is 138 millimeter. So we get the value of curvature as how much? 3.62 into 10 to the power minus 6 per millimeter. Why is the unit per millimeter? Because the strain is dimensionless and the value of the units of x is millimeter. Okay, so we have the moment capacity as 84 kilonewton meter and the curvature as 3.62 into 10 to the power minus 6 per millimeter. So option B is the correct response. Okay, so we'll proceed to the next question now. Now, the next question, for the rectangular RC beam given in question 6, what would be the moment and curvature corresponding to a concrete strain of 0.001? Okay, kindly take a few minutes and let me know what would be the correct response. Okay, so I think, yeah, again, the cross-sectional details of this particular beam is same as the previous question. I'm just going to draw the cross-section for the reference. Okay, and yeah, as I mentioned previously, for the previous question, the width of the beam is 250 millimeter, and the overall depth is 450, right? And the effective depth is 400 millimeter. And we know that AST is 1256.64 mm square, right? And we have certain material properties. F prime C is 30 MPa, and yield strength of steel reinforcement is 500 MPa. Now we need to determine corresponding to a strain of 0.001, what would be the value of the moment and what would be the value of the curvature. Okay, so we have solved using the equations in the previous question. Now we'll take the help of the Excel sheet in order to determine the moment and the curvature. Okay, so for this I'm going to write down an algorithm based on the problem that we solved previously. Okay, so the short algorithm that we're going to follow is that first we have the known value of epsilon c, known value of epsilon c, or if you're developing the moment curvature relation, if you're developing that outside question, so you're going to assume, or you're going to take a value of epsilon c. Okay, start from a small value. Then once we have the epsilon c, assume the value of x. Okay, assume the value of x. Then from that, find out the value of the resultant compressive force and the tensile force. Okay, so both of them need to match. Okay, so you need to iterate the value of x until cc is equal to t. Okay, I'm going to write a side note over here. Iterate the value of x until cc is equal to t. Then once we have cc is equal to t, once we have the value of cc is equal to t, then we need to find out the value of m and find out the value of phi. So what is the value of m? We can take that is cc into the lever arm, and then phi is equal to epsilon c divided by x. Okay, so this is the simple algorithm that we need to follow in order to obtain the value of the moment and the curvature. Okay, now let us take the help of our Excel sheet and try to solve the problem. So this is a simple Excel sheet that I prepared uh, for the moment curvature analysis of the flexural members. So we have the width of the beam, that is 250 millimeter. Then the overall depth is 450 millimeter, right? Then considering an effective depth of considering an effective cover of 50 millimeter, we obtain the effective depth as 400 millimeter. Then the area of steel in tension, that is 4 rebars of 20 diameter, that is 1256.64 millimeter square. Then we have the percentage of the steel reinforcement, that is 1.18 percent. Then we have F prime C as 30 MPa, then epsilon prime C as 0.002, and finally we have Fy as 500 MPa. Okay, then the longitudinal strain in concrete, we're going to increase it from 0.00052 to 0.001. Okay, then we are going to iterate the value of x until both the compressive force and the tensile force are equal. Okay, so we see that the CC is lesser than PS, so we are going to increase the depth of the neutral axis to 140. Okay, still CC is less, increase it to 150. Okay, now CC has exceeded the PS, so we need to understand that the value of x is between 140 and 150. Let us try 145. Okay, CC is still more. Reduce the x value 144, 450. Reduce further 143. Okay, so we need to again fine tune the value between 143 and 144. Okay, increase it slightly 143.6. Yeah, I think this is perfectly balances the compressive force along with the tensile force. Okay, right. So for this value of x 143.6, we already have uh, calculated, we already have programmed this Excel file in order to give us the value of the moment and the curvature. So the corresponding moment is 157 kilonewton meter and 6.96 into 10 to the power minus 6 per millimeter. That is the value of the curvature. Okay. Now, so now let us go back to the slide and look at the correct answer. Right. So the correct answer is option A. But however, once we have the value of x, let us try to fi find out the value of the m and phi manually now. So we have x is equal to 143.6 mm. Okay, x is equal to 143.6 mm. All right. So we have m is equal to cc into d minus beta 1 into x by 2. Okay, so we have cc is what is the value of cc? I'm sorry, the equation for cc. By the way, cc is equal to ts. Okay, so cc is equal to alpha 1 into f prime c into beta 1 into x into b. So we get the value of cc as per the Excel sheet 448.75 kilonewton. 448 448.75 kilonewton. Okay, and then we have d is equal to 400 millimeter. Beta 1, again we have used this Excel sheet to determine beta 1. Beta 1 is 0.7, right? And x is 143.6 millimeter. So when we plug all the values here, cc, d, beta 1 and x, we obtain the value of m as 156.9, 156.9 kilonewton meter. And then we have the value of curvature phi is equal to epsilon c by x, that is 0.001 divided by x is 143.6, which gives us a value of how much? 6.96 into 10 to the power minus 6 per millimeter, right? So option A is the correct response. So we'll proceed to the next question now. So again, for the same RC beam considered in the question 6, we need to determine the value of moment and the curvature corresponding to concrete strain of 0.0015. Okay. So initially we determined for epsilon c, we need to determine the value of m and phi. So this is what we are doing presently. Okay. So corresponding to 0.0005, then 0.001, 0.0015. We need to determine the value of m and phi. Okay. Then what we will do is we are going to plot this moment curvature curve, moment on the y-axis and curvature on the x-axis. Okay, this is going to give us some kind of a moment curvature plot. Okay, so this is the big picture. This is the ultimate objective of the problem that we are doing. Okay, kindly take a few minutes and let me know what would be the value of m and phi. Okay, sorry for that interruption. There was some connectivity issue. So, let us continue with the problem now, right? So, I hope, yeah, we'll make up for the lost time now, right? So, let us try to solve this example using the Excel sheet that we have developed, right? So, let me start sharing my screen now. Yes. So, yeah, I am sharing my screen. Let us go to the Excel sheet. Now, the Excel sheet, it's having a width of 250. Beam is having a width of 250 millimeter, depth of 450, effective depth of 400, right? And then now we'll choose a value of 0.00, sorry, 0015. Now, corresponding to a longitudinal strain of 0.0015, I'm getting the neutral axis depth of 149 millimeter. So, corresponding to a neutral axis depth of 149 millimeter, I'm able to balance the resultant compressive force in concrete and the resultant tensile force in the rebars. Okay, and for that, the value of moment is 217.6 kilonewton meter, and the curvature is 10.07 into 10 to the power minus 7. Okay, 217 and 10.07 into 10 to the power minus 6 per millimeter. So the correct answer for this particular question is option D. Okay, so I'm just going to give you the equation, right? So we have, what is the value of x that we got? X is 149 millimeter, right? And CC is equal to alpha 1 f prime c into beta 1 into x into b, which gives us a value of CC as 628.6 kilonewton, right? And M is equal to CC into d minus beta 1 into x by 2, which gives us a value of 217.6 kilonewton meter. And correspondingly, we have the curvature. So, yeah, we have the curvature phi is equal to epsilon by x is equal to 0.0015 divided by 149, which gives us a value of 10.07 into 10 to the power minus 6 per millimeter. This is the value of curvature that we are getting. Moving on, option D is the right answer. Moving on, consider the same rectangular concrete beam. What would be the moment and curvature corresponding to concrete strain of 0.002? Okay, so for a concrete strain of epsilon c is equal to 0.002, what would be the value of the moment and the curvature? Now, let us go back to the Excel sheet and try to find out the value of x, where uh, both the compressive and the tensile forces are able to balance. Okay, Now epsilon c is equal to 0.002, right? And we are able to balance, as we can see, the compressive force in concrete, it is much higher compared to the tensile force. So we need to reduce it, uh, and I'm able to balance the compressive force and the tensile force corresponding to a neutral axis depth of 125.6 millimeter. Okay, so the value of x is equal to 125.6 millimeter. Correspondingly, m is equal to cc into b minus beta 1 into x by 2, right? And we have cc is equal to, let me write down the expression for phi as well. Phi is equal to epsilon c by x, right? We have 0.002 divided by 125.6, right? cc is equal to how much? cc is 628 kilonewton, right? 628 kilonewton. So when we substitute the value of cc, d, beta 1 and x, we obtain the value of m as 221.6 kilonewton meter. And correspondingly, the curvature is nothing but 15.9 into 10 to the power minus 6 per millimeter. So based on the value of m and phi, we see that the option B is the correct response. So moving forward, right? So ultimately, we need to find out the m and phi corresponding to epsilon c is equal to 0.0035. I'm going to solve it quite quickly, right? So we'll go back to the Excel sheet, right? So 0. Oh, I'm sorry, 0.002. This remains the same, 0.0035. So we see that the value of C is higher than the TS. We need to increase, we need to decrease the value of X, and corresponding to X of 114.8, we're able to balance the compressive force with the tensile force. Okay. So we have Cc is equal to how much? 627.8 kilonewton. 627.8 kilonewton, right? Now we have the value of the equation for n is equal to Cc into d minus beta 1 into x divided by 2, that is 627.8 into d is how much? 400 minus beta 1 is 0.9. What is the value of x that we got? X is 114.8 divided by 2, which yields us a value of m is equal to 218.7. 218.7 kilonewton meter. Correspondingly, phi is equal to epsilon c by x, which gives us a value of how much? 30.5. 30.5 into 10 to the power minus 6 per millimeter. That would be the value of curvature. So we can see that option D is the correct answer. Okay. So as I already mentioned, in questions 6 to 10, we determined the value of m and 5 for different values of curvature, right? For epsilon c 0.0005, okay, 0.0005, 0.001, 0.0015, 0.002, and ultimately 0.0035. And correspondingly, we found out the values of m and phi, right? So for each value of strain, we obtain the values of m and phi. Now we are going to plot the moment curvature uh, curve, and this is how it is going to look like. Okay, the curvatures uh, represented as into 10 to the power minus 6 on the x-axis and moment on the y-axis, we obtain the moment curvature plot. Okay, so using this plot, we can see that the moment curvature plot is linear up to a curvature value of 10 to the power minus 5 approximately. Okay, so we can see that the beam is the beam as a overall component, as a structural component, it is able to stay uh, in the linear range up to 10 to the power minus 5 curvature, and beyond that it enters the nonlinear region. Okay, so and also we can say that corresponding to a moment capacity of around 220 kilonewton meter, it is in the linear range, and beyond that it tends to go in the material nonlinear range. Okay, so that is the based on the questions 6 to 10, we were able to perform the moment curvature analysis and plot the moment curvature curve for the reinforced concrete beam considered in question 6. Okay, now the question 12, you can say it is a continuation of the previous 5 questions that we saw. For the rectangular RC beam given in question 6, what should be the area of the reinforcing steel to achieve a balanced failure? Okay, kindly take a few minutes and let me know what would be the correct response. And while you are solving the problem, try to remember what is the definition of a balanced failure. Okay, that is the compressive failure of concrete occurs at the tensile failure of the rebar. Okay, I'm going to start drawing the diagram over here, right? As I mentioned, epsilon c is equal to 0.0035. That is the strain at which we are going to assume that concrete crushing happens. Concrete crushing. Pardon my poor handwriting. And epsilon y is equal to 0.0025. It is the point where the reinforcing steel yields. So the strain corresponding to which both the concrete crushing and the reinforcing steel yields, that is called as the balanced failure. Okay. So now uh, we have these two similar triangles, and we know what is the value of the effective depth. So effective depth D is equal to 400 millimeter. So from this, we need to determine we can determine the depth of the neutral axis. Okay. So from this neutral axis depth, we can find out the remaining aspects of the balance section. Okay. So let us first find out what is the depth of the neutral axis, right? That is epsilon c by x is equal to epsilon t divided by d minus x. Okay. So let us substitute uh, 0.0035 divided by x is equal to epsilon t is 0.0025 divided by 400 minus x. So solving this, we get the value of x as how much? 233.33 millimeter. X is 233.33 millimeter. Okay. Now we know the value of x, and we know that for any cross section to be in equilibrium, the resultant compressive force Cc should be equal to the resultant tensile force, that is Ts. Okay. Now let us go and find out those values, right? Now we have x is equal to 233.33 millimeter. Okay. And Cc is equal to Ts, right? I'll take another color now, right? We have Cc is equal to alpha 1 into f prime c into beta 1 into x into b. Okay. And Ts would be Fs into As, right? So considering uh, the value of epsilon c is equal to 0.0035, right? We can obtain the stress block parameters, that is alpha 1 and beta 1. Okay. So for this strain value, we have the value of beta 1 as how much? 0.9. Okay. Beta 1 is 0.9. I request you to just calculate the value of beta 1 based on the formula and see if you are able to get this value. And alpha 1 is 0.8102. Okay. We have alpha 1 and beta 1, and we know the value of x and we know the value of b. Okay. And we have Ps, and we know that here Fs is equal to how much? 500 MPa. So what we do is we simply equate Cc and Ts. Okay, let us proceed to do that calculation here, right? 0.8102 into f prime c is 30 into beta 1 is 0.9 into x is 233.33 into b is 250 is equal to Fs 500 into As. So substituting these values, we obtain the value of As, or the area of reinforcing steel, as 2552 2552.1 mm square. I hope that the explanation that I gave is clear. So by this, the result out of the 5 options, option C is the correct response. Okay, then we have calculated the percentage of the steel reinforcement as well. That is PT is equal to AST or AS by BD into 100. Okay, so let me check the equation for the PT. AST is, wait, 2552.09. Okay, so what is the PT is 2.6, right? Okay, 2.27, right? So here, yeah, C3 into C4. Okay. Okay, so the correction is for the percentage reinforcement, we need to consider the overall depth. Okay, please make that change. AST by B into capital D into 100. Okay. So for this particular question, option C is the correct response. So we will proceed to the next question. Okay, so for the balanced rectangular section given in question 12, what is the moment and curvature at failure? Okay, so we need to determine the moment and the curvature. Okay, so let us solve by considering the equations. M is equal to Cc into D minus beta 1 into x divided by 2, right? So Cc, what is the value of Cc? So yeah, we'll go to the Excel sheet here. So we have already substituted the value of AST and corresponding to the value of epsilon C is equal to 0.0035. We have Cc. Okay, we need to change the value of x to how much? 233.33. So we are able to balance the compressive force and the tensile force. Okay, Cc is 1276 kilonewton, right? Cc is 1276 kilonewton into D is 400 minus what is the value of beta? Beta is 0.9 into x is 233.33 divided by 2. So we get the value of m as how much? 376.4, right? 376.4 kilonewton meter. Again, I request all of you to check the values that we are getting, and phi is equal to epsilon c by x, that is 0.0035 divided by 233.33, which we get a value of 15 into 10 to the power minus 6 per millimeter. Okay, upon solving this, we get the value of 200 and sorry, m is 376.4 and phi is 15.06 into 10 to the power minus 6 per millimeter. So option A is the correct response. Okay. So we have 20 minutes and another 5 questions. So we'll proceed quickly. So for the balance section, so what we need to do is we need to consider different values of epsilon c, right? 0.0005, 0.001, 0.0015, 0.002, and ultimately 0.0035. Then we need to determine the values of m and phi. Okay, m and phi. Okay, then once we obtain the values of m and phi, we need to plot the moment curvature curves. or the moment curvature plots. Okay, for the balance section, that is AST is balanced. So let us see what is the moment curvature plot that we are getting. Right. So this is the moment curvature plot. Okay. So we can see that the ultimate curvature is less than what we obtained previously. So here it is 15 to 10 to the power minus 6. We'll be doing a comparison of the moment curvature plot of the under reinforced section and the balance section at a later question. Now let us see what is the next question. Okay, so for the same reinforced concrete beam, what is the maximum area of the what is the maximum permissible area of steel reinforcement that can be provided as per the IS 456-2000? Okay, so there are 6 options. Kindly take a few minutes and let me know what would be the correct response. Okay, so here it is nothing but 0.03 BD refers to 3% of the cross sectional area, 6% of the cross sectional area, and 4% of the cross sectional area. Okay, kindly have a look at the IS code provisions and let me know what would be the correct response. So as per the IS code, for a rectangular reinforced concrete beam that is subjected to flexure, the maximum permissible cross-sectional area of the steel reinforcement is 4%. That is, let us calculate what is 4%. 0.04 into 250 into 450, that gives us a value of 4500 mm square. So option E is the correct response. Okay, so we can see that the initial for the under-reinforced cross-section in question 6, we provided a cross-sectional area of 1256.64 mm square, and then for a balanced section in question 12, I think we provided 2552 mm square, and any amount of steel that is beyond the balance section, that results in an over reinforced cross section. Okay, and for this particular question 15, we are having AST is equal to 4500 mm square. So now let us determine the moment curvature plot and see how the behavior of the beam becomes if we provide a over reinforced cross section. Okay, so for the reinforced concrete beam given in question 6, if the maximum permissible area of reinforcement is provided, that is 4500 mm square or 4% AST, right, or 4% AST, for an axial strain of 0.0005, we need to determine the value of moment and curvature. Okay, kindly start solving the problem. Okay, we'll solve the problem simultaneously and obtain the value of m and phi. Okay, and the algorithm remains the same. So I'm going to just recap the algorithm to determine the m and phi once again. So we're going to take a certain value of epsilon c. So here it is 0.0005. Okay, assume a value of x or the neutral axis depth and ensure that you have to reiterate the value of x so that Cc becomes equal to Ts. And finally, we need to determine the value of the m or the moment capacity. Okay, moment capacity and the curvature phi, right? So let me go back to the Excel sheet, right? And we're going to solve the problem using that Excel sheet. So we have the geometric properties are the same, the width of the beam is same, total depth is same, then the effective depth is same. And now the AST becomes how much? 4500. So as soon as I enter the AST value, we can see that the percentage of steel has been calculated, that is 4%. Then the material properties are the same, F prime C 30 MPa, epsilon prime C 0.002, and the yield strength of steel is 500 MPa. And here we need to calculate the value of M and phi corresponding to epsilon C of 0.000005. Okay. Now let us see at what value of x the compressive and the tensile force can actually balance. Right. Now for 0.0005, we can see that Cc is higher than Ts. So we need to reduce the value of x. Let's see for 220. Okay, so for 220, we need to reduce it slightly further to 15. Okay, not so less, 218. Yeah, we need to slightly increase it now. So for 218.2 millimeter, for x is equal to 2.1, 218.2, we are able to balance the compressive force and the tensile force, that is 375 kilonewton. Okay, x is equal to 218.2 millimeter, right? Correspondingly, we are able to get Cc is equal to Ts is equal to 375 kilonewton. Now we need to find out the value of m over here. M is equal to Cc into d minus beta 1 into x by 2. So irrespective of the cross section that is provided, whether it is under reinforced or a balanced section or an over reinforced, under reinforced or a balanced section or an over reinforced, okay, the equation for the moment capacity is the same, right? So when we substitute the value of Cc as 375 kilonewton, d is 400 millimeter, beta 1. So beta 1 depends on the value of epsilon c. It is 0.68 and x is 218.2 millimeter. We obtain the value of m as how much? 122.12 kilonewton meter. 122.12 kilonewton meter, right? And the curvature phi, that is epsilon c by x, is how much? 2.3 into 10 to the power minus 6. Again, I request all the participants to verify these calculations when they are seeing the recording and let me know if there are any doubts so that we can discuss that in the upcoming sessions. Okay. So we can see that for the values of m and phi, option C is the correct answer. Okay. So moving on. Okay. So again, I'm going to uh, just recap what we are doing in today's class, right? So we considered one underimposed cross section, then we considered one balanced section, then we took one overimposed section. Okay, then what we did was we considered uh, certain strain in concrete, right? So I'm going to write it again. I'll take a different ink. So we considered different values of epsilon c, that is 0.0005, right? Then we considered 0.001, then we consider 0.0015, then 0.002, ultimately 0.0035, where we assume that the concrete is going to crush and the beam is not going to take any further loading as per our analysis. Okay. Then for these values of epsilon c, we determine the value of m and phi, moment capacity and the curvature, moment capacity, curvature, m and phi, m and phi, and m and phi. After that, we plotted the moment curvature curve. Okay, that is moment on the y-axis and curvature on the x-axis. Okay, so presently we are taking this over reinforced cross section. We are taking this over reinforced cross section, and then we plotted the moment curvature plot, right? So this is the moment curvature plot that we get for the over reinforced cross section that is considered in the question 15, right? Yeah, question 15. This is the moment curvature plot that we're going to take. Now, like we'll try to summarize today's class or today's live interaction session using another plot. That is, we are going to compare the moment curvature plots, as I said, for the under info section, then for the balance section, and then for the over info section. Okay, now I'm going to show the moment curvature plots for the under reinforced, balanced, and the over reinforced cross section. So this is the plots for the under reinforced beam, then the balanced beam, and the over reinforced beam. So we can see that we have different values of AST, right? So I'm going to just reiterate, just recap the AST once again. So for this, for the under info section, AST was 1256.64 mm square. And for the balance section, AST was 2552.2 millimeter square. And for the over info section, AST was 4500 mm square. So what we can make out from the moment curvature plot is that when the beam is under reinforced, right, the moment capacity is not significant, but it is able to achieve a very high curvature. Okay, so it is almost if we take the value of ductility, so ductility is the ratio of the peak curvature to the curvature at which the beam is considered to yield, and the value of curvature ductility is 30/10. So it is very important to consider a ductile behavior for the reinforced concrete structures, especially when we are designing for extreme loading conditions such as earthquake and wind. When we are considering the extreme loading conditions such as earthquake and the wind load, we want the beam or any reinforced concrete structural component to behave in a ductile manner. Okay. On the other hand, when we look at the ductility, by the way, ductility can be given by mu, that is delta ultimate by delta y, right? So ductility is almost close to 3. When we consider a balance section, we see that uh, the the deformability or the ultimate curvature does not extend much beyond the yield point if we consider this as the yield point. Okay, so again the ductility value is very less for the balance section, and this type of behavior is not really ideal for a reinforced concrete structural component. And then in an over section, any amount of AST that is beyond the balance section, that is called as an over section. Again, we see that the deformability expressed in terms of the curvature is very limited, and it is we can say that it behaves in a brittle manner, and that is not really ideal for any sort of a reinforced concrete structural component. Okay, so when we are designing any RC member, we need to behave it, we need to design it to undergo a ductile behavior. So we need to generally avoid, we need to take a hint from the moment curvature of today's example for the over section and balance section, and we need to avoid uh, the brittle behavior or the over or the balance section, and we need to design the beam as an under section. Of course, we can, if we want to improve the moment capacity, we can always provide the compressive compression steel, and we can augment the moment capacity, and we can also improve the curvature also. So when we'll see in the further classes that if we are providing a doubly reinforced section, we are able to achieve a higher moment capacity, and we are able to achieve a higher curvature also if we are providing a doubly reinforced cross section. Okay, but that will be the subject matter of the upcoming lectures. So the crux of today's lecture is that we need to design a reinforced concrete beam for higher ductility rather than higher moment capacity. Okay, if we need to improve the moment capacity, we need to go for a doubly reinforced cross section. That is, from the analysis, if we are able to, if we are getting that the moment capacity has to be improved beyond the singly reinforced cross section, we need to provide reinforcing steel in the compression area. So let me draw the diagram. In addition to AST, if the moment capacity is less than, if the moment capacity is less than the moment of the required moment from the analysis, or if the capacity is less than the demand, then we can improve the moment capacity by providing the steel in the compressive region. Okay, so that will be taken up in the further classes. Okay, so we'll proceed to the next question. Yeah, so again, I think this question is going to sum up today's discussion in a very precise and manner, which is going to reinforce our learning. So the question is, plot the variation of ultimate moment and ultimate curvature capacities for beams given in questions 3, 6, 13 and 16 with increasing area of the reinforcing steel. So again, I'll remind you that question 6 corresponds to under reinforced cross section, question 13 corresponds to a balanced cross section, and question 16 corresponds to an over reinforced cross section. Now let us look at the relation between AST and the moment and the AST and the ultimate curvature. Okay, so the blue curve here corresponds to the increase in the moment capacity, and the red curve here is corresponds to the variation of the curvature with AST. Okay, so on the x-axis we are plotting the area of steel. Okay, so we have three data points. Right? We have three data points over here for moment and the curvature capacity each. So when we increase the area of steel, the reinforcing steel, we can see that the moment capacity increases, which is desirable, but at the same time, the curvature is getting reduced, the ultimate curvature. Okay, so again, as I already mentioned, we need to increase the moment capacity, but without compromising on the curvature, right? So the if the demand is greater than if the demand is greater than the existing capacity, we need to go for a doubly reinforced cross section. Doubly reinforced cross section. Okay, so that is, that is the take home point from the today's discussion. So with that, I think we have come to the conclusion of today's. So this is again the slide from Sir's lecture today, in module 5. So we have seen that similar results were obtained from the example that he solved as well. So here this corresponds to under reinforced cross section, and the red curve corresponds to the balance section, and the black curve corresponds to the over reinforced cross section. And similar moment curvature plots were obtained from his lecture as well as the examples that we saw today. And again, this is the variation of the moment and curvature capacity with respect to the AST that is being provided. Again, similar behavior was we saw in our examples as well. And with that, um, I'm going to conclude today's live interaction session. And in next class, we're going to be dealing with flexural members, which are subjected to actual compression and which are doubly reinforced. Okay, I thank you all. And if there is any question or doubts, please feel free to comment on the recording of the YouTube video. Okay, thank you.